Hi everyone. So we're going to be talking about traveling salesman problem. Our group name is Traveling Salesman Looking for Polynomial Time Solutions. My name is Sunny Chung.
My name is Alex.
My name is Jesse.
So I'm going to be going over a brief introduction of what TSP is and the motivations. And we're going to go over three different algorithms to cover how this is solved. And with conclusion, we're going to compare and contrast each of the methods with its algorithmic complexity. So what is traveling salesman problem and why should we even care about it? So the problem can be easily stated with this question. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and return to the original city? This is similar to finding the Hamiltonian cycle, but except in this case, we want to find the Hamiltonian cycle that has the lowest weight possible. For a quick refresher of what the Hamiltonian cycle was, let me go through an example of what the Hamiltonian cycle may be. So in this case, if we're trying to find a Hamiltonian cycle, we're trying to see if there's a path that goes from vertex and then visit every single vertex, every other vertex in the graph exactly once, and then return back to the point. So in this case, it would be A, B, D, C, A, or A, D, B, C, and then back to A. And you see there are several different Hamiltonian cycles in this example. Traveling salesman problem is actually a typical example of NP problem, where many computer scientists have tried to find the best method that can solve for an optimal solution.
Right. So in terms of NP, there are three distinct categories. First is NP, which is short for non-deterministic polynomial time. This is indicative of a problem that is solvable by a non-deterministic Turing machine. In other words, an alternative way of thinking about this, though, is a solution that is verifiable in polynomial time. Another set of problems are NP hard problems, which means that these problems are reducible from problems in NP space. Another equivalent definition of this for our purposes, though, is that the problem is reducible from an NP complete problem. And then finally, an NP complete is a problem that is both NP and NP hard. So for the purposes of our NTSP, if it is an optimization problem, i.e. finding the minimized route, it is actually an NP hard. Why? This is because it is reducible from a Hamiltonian cycle problem, which is an NP complete problem. And there's also no way to verify the solution in polynomial time, because in order to do that, you would still have to enumerate all possible permutations, leading to an exhaustive search, which is exponential.
So far we've talked about what the traveling salesman problem is, and now we're going to be talking about why we should care about it. So there are a lot of practical applications with this problem. A typical example may be bus routing, navigation, or circuit board drilling. And to give a specific example on this, let's say you want a consulting firm and you want to save the cost of your employees traveling to each different cities where your clients are located so that the overall cost of running the business is lower. Throughout several different examples we're going to be showing, we're going to see how this is a very difficult NP problem where we're still not able to find an efficient solution that guarantees correctness. So we're going to go over a very basic algorithm that guarantees getting the right solution for the TSP problem. So the brute force is calculating all the possible routes and getting the route with the minimum cost. In this example, let's say we're traveling from the position 1 and then going through each of the nodes and then returning back to the node 1 or vertex 1. And so in order to get that, we will calculate 6 different routes that can be generated from this graph. So for this example, it can actually be just done with 3 since the last 3 and the first 3 are basically taking the same route except it's going in a reverse order. So let's say for the route 1, 2, 3, 4, 1 and 1, 4, 3, 2, 1 would have exactly the same cost because the direction is undirected. But in the real world situation where when we're trying to get the navigation, the distance from point 1 to point 2 will be different with the distance between 2 to 1, or the cost it takes to get to each point. That means we have to generate a n-1 factorial permutations. So in this case, there were 4 vertices. So we generated 6 different routes to get the minimum cost solution. So the time complexity with brute force is O of n factorial, and the space complexity is also the same. This is because we're measuring all the possible routes and storing each routes, so you get O of n factorial. And it guarantees correctness since it goes through all possible routes, but this is very inefficient when n gets larger and larger.
So in order to improve on the brute force algorithm, we use dynamic programming using an algorithm called the Bellman-Held-Karp algorithm. This algorithm depends on two propositions. So the first one is that the solution doesn't depend on the starting city. This means that when we're constructing the algorithm, we can start at an arbitrary city 1 and calculate a solution from there, and that will be the solution to the TSP. The second proposition is that every subpath in the solution is a solution to that respective subproblem. So this allows us to split the larger TSP into a bunch of smaller subproblems, which allows us to use dynamic programming. So commonly with the Bellman-Held-Karp algorithm, there's a distance matrix, which is just another way to represent the TSP problem. So it's an n by n matrix where each entry is the distance between the city I and the city j. So for example, the entry 1 means that the distance between city 2 to city 1 is 1 unit. So to use the dynamic programming, we define a recursive cost function. So the function is defined at the top. So in the function, I is a city that you're starting from. S is a subset of cities that you still need to visit. And then on the right side of the function, J is a city that is in the subset S that you will visit next. And then now your new subset is all the cities from before except for J because now you visited. And then you have to add the distance between I and J because that's the cost to go from city I to J. And then if S is empty, then the cost is just the distance to go from that city back to the starting point, because if there's no more cities to visit, you visited them all. So in order to finish the TSP, you just need to go back to where you started. And when doing the algorithm, we use a bottom-up approach. So we start with a subset of size 0, which means that you've went to every city and you just need to go back to where you started from. And then we slowly add more cities from there and build up to a subset size of n minus 1. And then we store the costs as we recursively calculate them in a lookup table in order to minimize the amount of calculations that we do. So here's a quick example. The matrix at the top is just the distance matrix from before. Like we said before, the first function call that you call the cost will be with the empty subset. So we're starting from city 1. So if you're at city 2 or city 3, that means you have to return to city 1. So the first cost function is just the cost to go back to the starting city, which we can find very easily with the lookup table, with the distance matrix. So then the next one is our subset, we add one city. So for the first one, you're at city 3, you still have to go to city 2, and then you have to go back to city 1. So again, we just use the function definition as before to calculate the values. But notice we're calling in the recursive cost function, cost of 2 phi and cost of 3 phi. And those are values we've already calculated before. So we can use the lookup table instead of having to do those calculations over again to quickly compute the results. And then in the last step, we build up to a size of subset of n minus 1. So here we have to there's 2 different options to go from city 1. You can either go to 2 or 3. So we have to calculate both of those possibilities. So we calculate if you go to 2 first or if you go to 3 first, and then we find the minimum of those values. So again, we're calling cost 2 and then set 3, or cost 3 and then set 2, which are values, again, we've already calculated in the step before. So we can use the lookup table again to minimize calculations, which saves time. Also, this problem is pretty simple because we wanted to keep it short. But if you imagine the problem was bigger, because in this one you're taking a minimum, you're essentially cutting out one path because you know that the path here, you're cutting out the path of going to 2 first because you know that one is slower than going to 3 first. So if you think of this problem as a subproblem and there's more cities to go for, if you ever reach this subproblem, you already know what the optimal solution is, so you don't have to check another one, which also makes this algorithm more efficient. So this recursive calls only calculates the results or the length of the TSP, but if we want the path, we just backtrack over the vertices. So we just find the order of the vertices that we called J. So in the first one, the first J is 1, and then that's where we started. And then the second one would be J equals 3 in the second cost function that we called. So then we go to 3, the third one J equals 2, and then the fourth one J equals 1 again. So here the path is just 1, 3, 2, 1. So for the analysis, the time complexity is O of n squared times 2 to the n. And this is because there's 2 to the n minus 1 subsets that we have to consider. And then in each subset, there's n items, at most n items. And we have to do n calculations on those n items. So that's how we get to the time complexity. For the space complexity, it's n times 2 to the n. And this is how many values that we need to store in the lookup table to make our calculations quicker. And then for correctness, it's guaranteed to be correct. We're still looking at technically every path, except we're selectively choosing some to like eliminate because we know that they're inefficient, but we're still going through and checking all of them.
So the last algorithm we're going to be talking about is 2-ops, which is a heuristic method. The idea is that edges that cross each other end up being more inefficient than edges that don't cross each other. So the idea is that we would take edges, switch them, and potentially uncross them, resulting in a better tour. The overall steps are pretty simple. So first, you would create a tour. It could be random, or it could be via another heuristic. And then you would iteratively pick edges and switch them. So you can see in this table or this picture here what that would look like, right? If A and D and C and B are initially connected, then you would quote unquote switch them by connecting A to B and C to D. Now, if this switch resulted in a tour distance that was less than the original distance, you would keep the new edges. And then otherwise you would just keep on picking edges, right? And then you would continue until there's no improvements remaining. So here's some brief pseudocode on this. I think it's pretty self-explanatory, but basically what happens is that as there are still improvements to be made, you would go through the number of eligible nodes and run the subroutine called 2-op swap, which would basically change out the routing you can see in that subroutine pseudocode. And then if that new route results in a better distance, you would keep it. Otherwise, you would start again. Now, this heuristic method actually has a couple interesting points. So first is that even though the worst case is still potentially exponential, i.e. in some scenarios you would have to consider every and all possible permutations, the average empirical case is that with an O of n squared per iteration, there's usually only a subquadratic number of iterations. So it's actually resulting in a fairly almost polynomial time. And then for space complexity, depending on the implementation, it could have potentially an auxiliary array for copying over the routing. So obviously over against all the other algorithms, this is far better improvement in both time and space, resulting in an efficient algorithm. The only problem is that there's no correctness guarantee. Unlike the other algorithms, because this is an NP hard problem, if we have an efficient algorithm, it may or may not actually result in the global optimum. However, empirically, what we see is that running 2-ops usually results in a result that is less than 10% off from the global optimum, and sometimes it even gets to less than 3 to 5%. In the practical world, this 2-ops algorithm is still better than trying to run the brute force or DP, as we'll notice in the summary slide. So here you can see kind of a summarization of all the different methods we've gone over: brute force with its factorial order of growth, DP with its exponential. Those are both going to be inefficient even when the cities get to like around 10 or 10 for brute force or 30 for DP, right? So for 2-ops, because obviously like there are going to be situations where you have a lot of different vertices, it is much more preferable because of its polynomial time. And even though it doesn't have a correctness guarantee, it's relatively close enough. Obviously, given that it's NP hard, there's like some strive to try and find an efficient solution with like better correctness bounds. But even like right now, 2-ops is still a very good practical element that's commonly used. And that's it. Thank you.